Good morning, everyone. I think we're going to try to get started now. So those of you outside, things are starting. It gives me great pleasure this morning to introduce the introducer, Professor Alex Vardy.
Hello, everyone. It is a great pleasure and a great honor to introduce our plenary speaker for today, Professor Avi Wigderson. Before I go on, let me just note that Avi is the last plenary speaker at this ISIT, and I will come back to this later. Well, Avi is one of only 8 permanent professors in the School of Mathematics at the famous Institute for Advanced Study in Princeton. I'm honored to say that Avi and I received our bachelor degrees from the same institution, namely the Technion in Haifa, Israel. Upon graduating from the Technion, it took Avi less than 3 years to earn his PhD in computer science from Princeton. Since then, for more than a quarter of a century, Avi has been a true trailblazer in the fields of complexity theory, combinatorial algorithms, graph theory, cryptography, randomness, and many other areas of theoretical computer science. His work has been recognized by numerous prestigious awards, including the Neven-Linna Prize, which is the counterpart in computer science to the Fields Medals in mathematics, and a plenary lecture at the latest International Congress of Mathematicians, and the Levy-Conant Prize, and the AMS Josiah Willard Gibbs Lectureship, and I could go on, except that if I were to describe all of Avi's honors, it would leave very little time for his lecture. So let me conclude this introduction with just one brief story about Avi. It is a true story, which I can certify since I have witnessed it myself. About a year ago, Avi gave a plenary lecture at a computer science conference in San Diego. After this lecture, a senior member of the community, whose name I will not mention, came up to Avi and thanked him profusely. "You see," he said to Avi, "I'm also giving a plenary here, and I was concerned that it is too technical. But hey, after hearing your lecture, I realize I have absolutely nothing to worry about." So the next day, that same person went ahead with his plenary presentation that consisted of some 50 densely covered slides, of which only the title slide had any actual words in English on it. So Avi, we have learned the lesson. We have scheduled you as the last plenary speaker at this conference. More seriously, though, we actually do like technical stuff, so you can have as few or as many formulas in your presentation as you like. We're absolutely delighted to have you here. Professor Avi Wigderson, please.
Thanks a lot for this welcome. I'll have to find a good story about Alex for mine. Don't worry, I have only 22 slides and I don't have many formulas there. I wouldn't change it now anyway. Okay, so I want to talk about randomness. I think this audience deals with randomness on a daily basis. Everybody has their own concepts and problems with it. And what I want to focus on is the computational complexity aspect of randomness, the algorithmic power of randomness. So let's see that it works. It was working. Okay, I have to be close. The plan, can one lower a little bit the lights in my eye? Okay, thanks. That's the plan of the lecture. I'll give you a very quick introduction to computational complexity, talk about efficient algorithms, and talk a little about the P-versus-NP problem, which is somehow relevant to the issues at hand. Then I have 2 main parts to the talk. One will be on the power of randomness, and the next will be on the weakness of randomness. And this dichotomy I'll try to explain. And in particular, we'll need somehow to define randomness in this context of computational complexity. And finally, I'll talk about randomness in other models of computation, in particular about proof systems. Okay, so let me start. So in computational complexity, we really want to find good algorithms for important problems, and we want to distinguish those easy problems from hard ones in a mathematical sense. And the way we view it is asymptotically. I'm sure that many of you are familiar with, so I'll just define it by example. Here's an example of an easy problem. It's multiplication. I give you two numbers. You want the product. That's something that we learn how to do in second grade. And if we look at this algorithm, we see that if it works on numbers with n digits, then the number of steps is roughly grows quadratically with the data size. So that's polynomial growth, and that's kind of problem we say is easy, is implementable, is efficient, and the class of problems containing such easy problem is P. On the other hand, we have the problem of just inverting this process we just described, factoring problem. Given a number, find its prime factors. The best algorithm we have so far for this is exponentially in the number of digits. And this is extremely slow if you work even on 100 or 1,000 digit number, which is a small number. And so if exponential was the best we could do, then we would say it's a hard problem, it's infeasible. Of course, we don't know that. Nobody knows that it's really difficult. We believe it's difficult. I mean, all of you believe it's difficult whenever you use this, you buy with your credit card on the internet. I mean, that's what underlies current security of cryptography and electronic commerce. But we don't know that. But I just want to say that if the running time, the best running time for a problem is exponential, then we call it hard. By the way, for information theorists, I think it's really good to notice this dichotomy between the information theoretic view and the computational complexity view of two pieces of equivalent information. A number and its prime factors are two pieces of information that information theoretically are equivalent. You can get one from the other. However, computationally, they are very asymmetric. It's much easier to get the product from the factors than the factors from the product. So that's of course, the key to cryptography. There are many other problems that are easy and many other problems that are hard or seem to be hard. And let me give you just one more example. This is the example of map coloring. And it also somehow demonstrates that it's hard to tell when a problem is easy or hard. So I give you a map without the colors, actually. And I can ask you some computational questions about it. For example, can you color it with two colors? And it's an easy problem. I mean, if you've never seen it, just try it. Sort of a greedy algorithm is very efficient here. But if I ask you whether this map is three-color, this or any map is three-colorable, this we have no efficient algorithm for. Somehow changing 2 to 3 makes a difference, and it seems like a hard problem. And we can change it again. We can ask whether this map is four-colorable. And again, this complexity changes dramatically and becomes a trivial problem because every map is four-colorable. So telling whether a problem is easy or hard is a hard thing. Anyway, I want to focus on three-coloring because three-coloring, as I say, we think it's hard, we don't know. And factoring, we think it's hard, we don't know. So we don't know how to answer either, but we do know in computational complexity some connections between them. And for example, here's something, if you haven't seen, it should surprise you. If there's a good algorithm for three-coloring, then there is a good algorithm for factoring integers. And such connections come from the theory of NP-completeness, in particular from the fact that three-coloring problem is NP-complete. And so for those of you who want to remember an easy way to state the P versus NP problem, it's whether three-coloring has an efficient algorithm. That's an equivalent formulation. Of course, it's about much more than this, and I will not go into it, but somehow captures the question of whether creativity, mathematical creativity, can be automated. But it's a topic for a different lecture. What I want to get out of this is that there's this list of problems that seem difficult, for which we have only exponential time algorithms, like I mentioned, factoring, three-coloring. You can talk about satisfying Boolean constraints. You can talk about finding the distance of a code. You can talk about computing optimal strategies for games. All these problems seem extremely hard, seem to require exponential time. And the question, perhaps the most fundamental question of computational complexity is this exponential time or size, if you're dealing with the hardware, is it necessary to solve these problems, or to solve at least some of these problems? And I would say that there's a consensus, more or less, that the answer is yes, that some of these problems are hard. So we don't know how to solve this problem, but that's a conjecture I want you to remember. I'll come back to it in a few minutes. Some of these problems, some NP-complete problems, say, require exponential time. OK, let me now move to the real issue of this lecture, which is randomness. So first, as I said, there'll be two parts. The first part just demonstrates that randomness seems like an extremely useful thing to have if you want to solve problems. So I'll just give examples of problems for which we have efficient probabilistic algorithms, but no deterministic algorithms so far. So this will show that, well, randomness seems powerful. Just to make sure we all agree on what a probabilistic algorithm is, so that's an algorithm that can use, a long sequence of independent unbiased coin tosses in its decisions. And such an algorithm has to guarantee, of course, the outcome of such a process is a random variable, so we want this random variable to give the correct answer almost surely, and then it becomes a good probabilistic algorithm. So all the algorithms I'll talk about have this property. And, well, for those, in this audience, I think people use probabilistic algorithms all the time. But just in case, why tolerate errors in algorithms? Of course, it's better to have 100% guarantee. But there are many places where we tolerate uncertainty, and we can tolerate it in algorithms as well. The nice thing about errors in probabilistic algorithms is that you can decrease them as much as you want just by repeating the algorithm many times. So that's an important feature. And of course, the reason, again, is that by using randomness in algorithms, we seem to get much more. So that's really the reason. So let me give you 4 examples of probabilistic algorithms that seem to have no deterministic counterparts, no efficient deterministic counterparts. There are basic problems in different areas. And I could give many more examples, but I think the point will be clear, and maybe is clear already. OK, so let me give an example from number theory. Actually, the best example we always had, and we kept repeating, was taken away from us a few years ago. This is a primality problem. Given a number, let's say n-digit number, is it a prime? There was this breakthrough in the mid-70s of this finding a probabilistic algorithm for this problem was so important that it was, of course, essential for cryptography. It's used all the time. And it actually started the field of probabilistic algorithms within computer science. And it was an example of something we couldn't do deterministically until a few years ago, when Agarwal, Kayal, and Saxena found an efficient way to do it. So it stopped being a good example for my lecture. However, just by changing it a little bit, we have a good example. So here's another problem. I give you n, just the number of digits, and I ask you to provide me with an n-digit prime. OK? Well, probabilistically, it's trivial. You just pick numbers at random, few numbers at random, just because of the density of primes. One of them will be a prime, and you can verify that using that algorithm. But if you want deterministically to generate an n-digit prime, the best known algorithm is the exponential. So there's a huge gap. So randomness seems powerful here. Let me move to another example in a different domain, algebraic. I'm sure many people have seen this, so it's phrased as a question. Is the determinant of this Vandermonde matrix equal this product? And I'm sure that many of you know that the answer is yes. It's a theorem of Vandermonde, very old. What I want to look at here is, how did he know that it was true? How do mathematicians prove algebraic identities? Well, this particular one is really easy. It's really easy. But suppose you guess or you observe that something should look like, it looks like an identity. And you want to prove it. You can't prove it. You want to at least gain some confidence that it's true. So let's formulate this problem. I give you a polynomial like this determinant here. And I ask in many variables, and I ask, is it identically 0? Well, you could, of course, expand the polynomial and check that all coefficients are 0, but that's a very inefficient procedure because in many variables you have exponentially many coefficients. So that's a bad way. And actually, it's not clear unless you have randomness, in which case the answer is obvious. I mean, you just plug random inputs to the polynomial, just evaluate it, right? And in fact, you can pick it from a small set of integers, these random values you plug in. And two things are, well, one thing is completely obvious. If the polynomial is identically 0, you always will get zeros, no matter what you plug in. If it's not identically 0, it turns out you can prove it's not difficult that almost every input you'll plug in will give you a non-zero output. So it's an extremely fast and simple probabilistic algorithm. If you want to do it deterministically, the best algorithm known is exponential. So again, it seems like a good example. And well, there's more you can do here. Let me give you a problem that's even closer to your heart, sort of analytic, for your analytic. It's a problem just of finding the large Fourier coefficients of a signal, which is given implicitly. So we have a function, let's say, on the Boolean cube that is given by a circuit or by a formula, and you want to know the top elements of the spectrum. You have some epsilon parameter, threshold parameter. You want all the Fourier coefficients above epsilon. Now, there are possibly 2 to the n Fourier coefficients. It's a function, the space is of size 2 to the n, but because of orthogonality, the number of such coefficients above epsilon is at most 1 over epsilon squared, so it's a small number. So you can, at least in principle, produce this list. The question how to do it efficiently, if I just gave you a formula for this function or a circuit. And again, it's not clear, and it's not even clear probabilistically, but there is a probabilistic algorithm, and it's not as simple as the previous ones I talked about. But that's a Goldrach-Levin algorithm, and it produces the large Fourier coefficients very efficiently in polynomial time in n, not in 2 to the n. And there are extensions of it to any abelian groups. And again, I'm just repeating myself. If you want to solve this problem deterministically, the best way we have of it is just more or less try all possibilities, work in time 2 to the n. So again, it seems like randomness gains you exponential time saving. And the last example is, again, very different geometric example. And, well, it has the same moral, but anyway, it's a really interesting problem, so let me tell you about it. Here the problem is estimating the volume of a convex body in very high dimensions. It's, again, a very basic problem. And I say estimate because we know that computing exactly the volume of such a body, let's say the body is given, it's a polytope, it's given by linear inequalities. Computing it exactly is harder than NP complete, so we know we can't do it, but let's say get the answer within a factor of 2. And so here's this polytope, but think about in many dimensions, so it's really, well, I couldn't draw it, obviously. And there's this wonderful algorithm, in fact, a series of algorithms starting with these people, which works roughly as follows. You want to approximate the volume, so it might as well approximate the number of grid points in a fine grid that you put in space. That's doesn't help much yet because in high dimension there are exponentially many potential points. And then you observe that there is a connection between approximately counting the number of elements in a set and roughly uniformly sampling from this set. So if you could get a random, uniformly random point, grid point in this set, then you'd be done. But how to do it? And here just throwing darts doesn't help. And what you do is actually take a random walk in this. You just start anywhere inside. I hope this red is visible. And you just, whenever you step out, you come back. And it's clear, it's really easy to see that such a random walk will converge to the uniform distribution. What's far from clear is that it will converge quickly. And that requires quite a bit of analysis. And I will not, of course, go into this. But it's a wonderful probabilistic algorithm. It has lots of applications. And it's another demonstration of the fact that, well, again, if you want to solve it deterministically, the best way, just even approximate the volume, the best algorithms we have are exponential time. So I think I repeated myself 4 times, which is enough. There is a huge list of problems for which we have fast probabilistic algorithms and for which the best deterministic algorithm is exponentially slower. That's why we think that randomness is powerful. So let me phrase it as a fundamental question. Does randomness help? Is it really powerful? Or maybe we are just stupid. We didn't find the deterministic algorithms yet. And these examples and dozens of others like them suggest that the right conjecture here is, again, yes, randomness helps. OK? So let me take you back to the first problem that I discussed. This is about the computational complexity of these problems in NP. The question was, did some of these problems, like map coloring and factoring and finding distance of codes and so on, some of them require exponential time or exponential size? And again, I said the conjecture was, yes, it seems that some of them must be difficult, otherwise we would have solved them long ago, especially the NP-complete ones that are connected together. They are all easy together or hard together. So these are 2 conjectures. They seem to talk about completely different objects. One's the power of randomness, and the other is sort of the power of non-determinism or guessing. And the main message of this lecture, if you want to remember one sentence, is the following. This is a theorem that we can prove. These 2 problems are not only related, they are, somehow. One of these conjectures is, has to be false. It's impossible that the answers to both questions is yes. Okay? So if randomness is powerful, then all these problems are easy. But on the other hand, if one of these problems is hard, then randomness is almost useless. So this is really mysterious if you have never seen it. And I'd like to just try to explain to you some of the ideas that go into the proof of such a result. I mean, what is the connection? What's the connection between computational difficulty and randomness, and algorithmic randomness? Okay, so that's what I want to show. So let me restate it, this connection between computational hardness and randomness. And it's taken up maybe 15 years to understand. And the basic message, as I said, is that of this kind. Maybe I should just make sure that we know which one is false here. Okay. The one that's false, that at least what we believe is false, is the first one. We really believe that randomness is not powerful, and I'll explain why computational hardness can be used to eliminate randomness, and that's computational hardness we believe in. We believe that P is different than NP. Okay, so The basic message is that if we have some natural like problems like map coloring or NP problems, if any of them is difficult, then we can take any probabilistic algorithm and remove the randomness from it. We can eliminate randomness from all efficient algorithms. So that's the main message informally. Formally, there are many statements. Let me give you one here, which is perhaps the strongest, is that if problems in NP, some problems in NP require exponential size circuits, then for every one of the probabilistic algorithms I showed you, and for any other efficient probabilistic algorithm, you can replace it with a deterministic one that also runs in polynomial time. That's also efficient. So you can remove randomness from all efficient probabilistic algorithms. All you need is one hard problem. So I want to sort of prove it to you. Okay, so the next like 5 or 10 minutes are the proof of this. Well, the ideas in this proof. It's taken many years, but I want to distill some of the essential ideas here. So I want to make sure that the statement is clear. If there's one hard problem, let's say factoring is hard, then in all the probabilistic algorithms I showed you, you can replace you can run them somehow without the randomness. You can have equivalent deterministic algorithms for them that are efficient. Okay, so let me try to do it. Okay, so what's a probabilistic algorithm? It's a program. Program takes an input, and on top of the input, it takes these random coins, these random bits, this uniform distribution, and it uses it to produce the output. And the output is correct, as we said, with very high probability. We want to be able to run this program without the random input. So it's not clear how to do it at all, and a huge leap is to actually do the following. Consider what happened to this same program if we run it not with the uniform distribution, but with some arbitrary distribution on the coin tosses. Okay? It's a mental experiment. Why not do it? Of course, you can do it. You can try to see whether your algorithm, how it performs when the coin tosses, the coins are antique. They maybe have dependencies, correlations, and so on. For every such distribution, the algorithm will do something. Sometimes it will do well, sometimes it will not do well, and so on. So what we want is to capture the distributions for which this algorithm, and in fact, any algorithm would do well, and call them pseudorandom. Okay, so here is the crucial definition. A distribution is pseudorandom if no matter what efficient algorithm we use, and no matter what input we feed it, the output will be distributed as if we fed the algorithm with a pure random coin tosses, with a uniform distribution. Okay, so again, pseudorandom distributions are those which fool all efficient algorithms. So for those of you, if you think about the standard metrics on probability distribution that you use in information theory, the L1 metric or divergence and so on, here we look at a huge coarsening of this. We don't care about the existence of events that separate one distribution from another. We care only about events that are efficiently testable, that are efficiently computable. So these are the efficient algorithms. We care only whether efficient algorithms will tell apart one distribution for another. Okay? And this is a really important definition. Once we have this, well, we know that if we have a pseudorandom, we might as well eliminate the randomness from a pseudorandom distribution than from the uniform distribution, because they cannot be told apart. And that's exactly what we want to do. We want to somehow deterministically generate a pseudorandom distribution. Okay, it's as good as a random one. So we want to generate it without random bits. We want to start with no bits and somehow generate efficiently and deterministically, a pseudo-random distribution. well, to an audience like this, it's clear that something is wrong here. I start with 0 entropy, and I generate even some entropy. It doesn't make sense, so let me help myself and say that we can actually start not with no random bits, but actually with few random bits. Few is very few, exponentially fewer than what we need. We need n random bits. Let me start with some log n random bits. And the reason it's a fair assumption is that log n random bits is something you can try all the possibilities of, right? So it's just, you can try all possibilities on this k bits in polynomial time. So again, what we want to do is start with few purely random bits, very few, and generate from them a pseudo-random distribution, deterministically and efficiently. If we can do that, it's called a pseudo-random generator. So that's what we want to do, and the way we are going to do it is, well, somewhere we have to use our assumption. So we are going to use the hardness of some function in order to construct such a pseudo-random generator. So I promised that what we needed is to generate from very few, from k random bits, logarithmically many bits. We generate huge number, n random bits for our algorithm. But actually, what I'll show you is something much, much simpler. It's just how to generate k plus 1 bits, just a little bit more than you had. Once you have this, then there is this NW generator that I will not describe that lets you amplify this result. So how do you generate just one extra bit? How do you start from k bits, which are pure, excellent, uniform, and generate from them k plus 1 that are indistinguishable from uniform by efficient means? That already looks manageable. First of all, you have k random bits where you can use them, so why don't you plug them in? So your problem is really just generating the last bit in a way that will be indistinguishable from random, unpredictable from its predecessors. And you have to do it deterministically. Well, if you have to do it deterministically, you just have to apply some function. And this function will indeed be the hard function that we assume is exponentially hard in the hardness assumption. Now, there's a slight, we need hardness in a different sense than usual here. We don't want just that it will be hard to predict sometime. We want that this last bit will look like a 50-50 coin toss, and therefore we need this function to be really hard, extremely hard on average, not just hard in the worst case. And that's another issue of hardness amplification. That's a big issue which I'm not going to describe. But if we have this hard function, we can extend k random bits to k plus 1 pseudo-random bits, and using this NW generator, you can amplify to many more bits. And so we can get from hardness such a pseudo-random generator that generates pseudo-random sequences which are indistinguishable from random sequences, and therefore can fool any efficient algorithm. So what's the summary of this de-randomization process? What we do is when we have an algorithm and we want to remove the randomness from it, we look at this generator, we try all possible seeds of the generator, of which there are just polynomially many. For each of them, we get a sequence. We feed the sequence as if it was a random sequence to the algorithm. We try them all and take a majority vote. Because the behavior of the output under pseudo-random and random distribution is the same, up to almost the same, then the majority vote will give always the correct answer. Okay, so it must have been somewhat quick, but hopefully you got some of the ideas of this connection, how hardness enables the generation of pseudo-random sequences for efficient algorithms. I want to mention that a very important point, in fact, that this idea of removing randomness via pseudo-random generators for this task of de-randomizing all algorithms required an assumption, a hardness assumption. But you can try to use this. It's a paradigm which you can try to use to remove randomness from specific algorithms rather than from all algorithms. And then maybe you can use fewer assumptions, weaker assumptions, or no assumptions at all. And in fact, it's a very successful paradigm. And the result I mentioned earlier about the deterministic primality test was obtained exactly like that. A deterministic algorithm to test primality was obtained by de-randomizing a specific probabilistic primality test with no assumptions. There's another one that I'll mention soon in a completely different context of maze exploration. Okay, so the bottom line is if you have hard functions, you can construct these pseudo-random generators and use them to remove the randomness from every efficient algorithm. Okay. Let me conclude with talking. So far, I talked about the issue of using randomness to save time. Is it possible or impossible? So the power of randomness was tested in saving time. Randomness occurs in lots of, lots of computational models, and you can ask the same question in others. Let me tell you about two others, one about saving memory, and then I'll talk about proof systems. Okay, so what is this maze exploration? Well, this is a problem that we are all familiar with. We come to Toronto maybe the first time. I should probably say Seoul. Next year in Korea would be more challenging maybe. You arrive there, you've never been there, and you want to find your hotel. You don't have a map, you don't speak the language, and what do you do? There's a, so that's a problem, and well, as you know from the maze in the picture, it's a very old problem, and one solution, it's really beautiful, is that maybe you should go to a pub, have a few beers, and then start walking in the city. It will be pretty random, and actually it will be good because a random walk in such an undirected graph, in such a maze, is guaranteed to find you not only your hotel, but in fact every hotel. You will and quite efficiently. I mean, if there are and corners, you'll in n squared time, you'll be exploring this graph with very high probability. So that's a fantastically strong and useful probabilistic algorithm, and you don't need memory for it at all. And it was a basic question for about 30 years. So whether randomness is essential in this kind of setting, when the problem is memory and not, the limitation is memory rather than time. And it was resolved, that's a breakthrough result of Reingold just about 2 years ago, that there's a deterministic sequence that can be computed again with more or less no memory, logarithmic memory, that will explore this, this maze or any city efficiently, without coin tossing or beer. And again, the solution is a pseudo-random generator, which is tailored, to this kind of setting. It's very different than the previous one I showed you. And it's also based on something that's very different. It's based on a certain construction of expander graphs, and not on hardness assumptions. But and these expander graphs can be constructed. You don't need assumptions for them. So the upshot is, this probabilistic algorithm can be de-randomized without any assumption, but using still the paradigm of computational pseudo-randomness. Okay, finally, let me talk about the last 10 minutes. I want to talk about randomness in proof systems, which is a very different game than algorithms. This idea of introducing randomness to proof systems is in these two important papers. And to talk about probabilistic proof systems, I have to talk first about deterministic or normal standard proof systems, mathematical proof systems. Well, first of all, what are proof systems for? Well, they are for proving theorems to find out the truth. And the sort of one input to a proof system is a claim. The claim we want to check whether it's true or not. Can be Fermat or can be, well, you can put what you like there. And then the most important object in a proof system is the verification procedure, the way we verify proofs. So a verification procedure is an efficient program has to be efficient. All proof systems in mathematics have efficient verification. In fact, nobody can, there's no point imagining verification procedures which are not efficient. What would we do with them? A verification procedure takes two inputs, a claim to be proven and the argument that supposedly proves it, and checks, right? And it has two properties that are standard properties, soundness and completeness. One, completeness says that if the claim is true, then some argument proves that it's true. That's a good case where we call the claim a theorem and we call the argument a proof. And on the other hand, you cannot be fooled by a false argument. So if the claim is false, then no matter what you put in the argument, the verifier will reject. Right? So these are the two standard properties of proof systems. And now let's talk about probabilistic proof systems. So in probabilistic proof systems, we do what we did with probabilistic algorithms. There is an algorithm here, the verification procedure. We allow it to be a probabilistic algorithm, to use random coins. And again, the outcome is a random variable, and what do we demand from this? When do we call it a good probabilistic proof system? Well, we want that if the claim is true, then this verifier accepts with probability 1. Okay? But if the claim is false, then we allow the verifier to make a mistake with tiny probability which can be decreased arbitrarily, but there's still some possibility of error that the verifier will accept a bad argument as proof. Now, from the mathematical viewpoint, this is terrible. I mean, why? We are after the truth. Why should we allow errors in proofs? And of course, this is not used to prove mathematical theorems. There are other uses that I'll mention in a second. It's a very important extension of proof system, as you'll see. But the main reason we do it is like we did probabilistic algorithms. We want to get more. So let me talk about what magical properties can you get from probabilistic proof systems that you cannot get from normal proof systems. So here we know that randomness helps. It enables to do things that are simply impossible without randomness. And I want to demonstrate it on two proof systems. Again, these two topics, or each one of them, would make a wonderful 1-hour lecture, but I'll give you just one slide on each. Probabilistically checkable proofs, PCPs, and zero-knowledge proofs. So there are different probabilistic proof systems. I'll tell you about each. And in each of them, the randomness enables to obtain a property that is impossible to get with normal proof systems. So let me tell you about both. So first, probabilistically checkable proofs. What are they? So in both cases, you should think of there is some claim, like maybe the Riemann hypothesis, and some prover, somebody wrote a paper about it. That's the argument. And then we want to check that it's true. So in PCPs, the concern we want to help with is the concern of the verifier, maybe the referee who has to read these 500 pages and find out if the proof is correct. So here's the restriction on PCP. PCPs allow the verifier, the referee, to pick at random some 10 locations or 100 locations, bits in the proof. Doesn't matter how many pages it is. Just look at them and just decide according to them whether the proof is correct or not. So the verifier is restricted in that way. It has to make a decision based on a tiny, tiny fraction, a constant number of bits in the proof, no matter how long it is. So I think most mathematicians that hear this, say, well, this is ridiculous. This proof system can do nothing. I mean, there can be one tiny lemma that's incorrect somewhere. You'll never get to it if you are looking only at 100 bits. That's a bad intuition. That's wrong. Here's a remarkable theorem that was proved about 15 years ago. It's not a useless concept, it's a universal concept. Every proof, every mathematical proof can be converted, can be transformed into another proof for the same theorem which can be verified by such a limited verifier. So again, if you so you can, if you force authors to write in this PCP format their proofs, which they can, in fact, they can automatically convert their proofs to PCP format, then verification can randomly select a few bits in the proof and decide according to them, and will not be fooled except with extremely tiny probability. This can be done for every mathematical theorem. And of course, the use of this is not for refereeing. I don't think it was implemented by anybody yet. But it's extremely important in an area that was, the connection is not quite clear, and it's very beautiful to proving hardness of approximation algorithms. So it's a major result in theoretical computer science. That's PCP. So here randomness does, amazing magic. Here's another place where randomness does magic, zero-knowledge proofs. Again, we are in the same setting. There's somebody who claims they proved the Riemann hypothesis, this prover, and then the verifier wants to verify this. But here the concern we want to address is not the verification, but the sort of paranoid concern of the prover, he or she wants to convince the verifier that they have a proof of the Riemann hypothesis, but they are really worried that the verifier will, read it, understand it, and rush and publish it on their own name. And, well, you can think of it as a copyright issue. So how can the prover protect himself against such an event? Well, here's a possibility. Suppose he could convince the verifier that the proof is correct without giving any information at all about what the proof is. That's zero-knowledge proof. It seems, I don't know, as useless as before, or as impossible as before, and probably you can guess that if it sounds as impossible as before, it can be done. And in fact, it can be done, and it can be done for every mathematical theorem. Every mathematical theorem for which you have a proof, you can convince somebody else of the correctness of the proof without giving them any information about this proof, if you have randomness. And here, this is different than the previous result. That's a conditional result. Here you need the cryptographic assumption. Here you need something like factoring is hard, or something standard we use in cryptography. And again, it's not used for this paranoia of mathematicians. It's used in cryptography, and that's a major application of these zero-knowledge proofs. OK, let me conclude. This talk focused on randomness, what happens to randomness when you view it through this limited computational complexity glasses. You care only about what happens to efficient procedures. The same things can be done and is done to lots of other important notions like learning and knowledge and proof. And you often get different meanings to these very basic concepts. For randomness, we saw that this definition of pseudo-randomness was sort of saying that randomness is in the eye of the beholder, or rather than the eye in the computational power of the beholder. Things that are obviously non-random from the entropy viewpoint may look random if you don't have enough time. And we saw that computational hardness can be used to generate good enough pseudo-randomness, which had the consequence that maybe probabilistic algorithms are not as powerful as we think they are. In some specific cases, this can be proved. In some specific probabilistic algorithms, we can remove randomness, and this led to great results. And on the other hand, in some other settings, like I showed you in proof systems, randomness seems to be absolutely essential. So all these wonderful things leave us with the same problems I started with. We have to know, we have to find out, we have to prove that some problems are hard. It would be great to prove that, let's say, factoring is difficult and their cryptography would rest on solid foundations. It would be great to prove that P is different than NP. But anyway, these are still open. We are looking forward to your help with them. Thank you.
Yes, you mentioned that there is a symmetry between the complexity of multiplication and the complexity of factorization. And here we are talking about operations on the integers, which is a ring, okay, or in the case of real numbers, it is a field. And how does the structure of rings or number theory come into the picture?
So the only computation I was talking about here is digital computation. When you operate on bits, these bits can encode numbers in a ring, in a field. They can encode graphs. They can encode lots of objects. It doesn't really matter. We think that no matter how you use these bits in the numbers given, whether you use the field structure, you use whatever you like, at least common belief so far is that factoring is difficult no matter what you do. I don't know if you wanted to contrast it with real computation, with working on real numbers, which I didn't discuss. Well, in my personal belief, real numbers are not real, and they just don't exist. There's nothing like real computation. I think all computation is digital. I think the real, the view of real and continuous space is extremely powerful, of course, in mathematics, and we use it all the time. There are definitely models of computation that work with real numbers, and the fair ones, you can allow fair or unfair operations. Well, anyway, it's a complicated subject. There are models. It's being studied, but I don't know of any relevance of it to these computational problems I discussed, and in particular, let's say, to the complexity of factoring. There's also quantum computing, but yeah, maybe if I must.
Other questions?
Yeah. Sorry. Sorry, I didn't hear. For which algorithm? For the first problem, well, I think that probabilistic algorithms existed long before algorithms were formulated. I think that the use of the law of large numbers in statistics, the use of sampling is probably the oldest idea of roughly counting something, is a probabilistic algorithm, and it's used as a very fundamental, there are basic facts, which is this law of large numbers. So I think it's as ancient as anything else. So before work in theoretical computer science, I think that most of the probabilistic algorithms were used either by statisticians and by physicists who are using Monte Carlo methods. So the Monte Carlo method was invented, I don't know, in the 50s and, well, actually earlier, 40s. What happened in the 70s and 80s is that for basic optimization, combinatorial problems, very concrete problems that occur in industry and computer science, the algorithms were developed, and this field grew and became very, very sophisticated.
In your introduction, you mentioned strengths and weaknesses of probabilistic algorithms. I haven't heard that much about weaknesses.
You didn't? I just didn't. Well, the weakness was the part which said that you can remove randomness from all probabilistic algorithms if you just believe that map coloring is or that P is different than NP, more or less, to be.
Oh,
yeah.
I see.
So it's all this strength is just a figment of our imagination.
Okay.
Okay?
Thank you.